Welcome to this eLearn Security video training lesson on web cracking. In this video, you will learn how to exploit web vulnerabilities in order to discover the network key. We will examine various scenarios that you could encounter when doing real-life penetration testing. We have set up our environment with a test access point using WEP as a security mechanism. As in the previous videos, the SSID is lab network. Correct configuration of your wireless monitor interface is also a prerequisite for this video. So please go back to the course slides in case you have not done it yet and review your settings. We will start with the preliminary recon phase, examining the neighboring area in order to detect the available wireless networks. From a terminal window, let's launch AeroDumpNG listening on our monitor interface. Let's run the command. You can see that our lab network correctly shows up in the command output, and it's correctly reported as a WEP network. Channel number is 11. However, we aren't able to detect any associated clients communicating with the AP. This is probably due to the low traffic and short channel hop interval. To discover associated clients, let's focus our scan on the proper channel. Let's write AeroDumpNG -C 11 mon 0 to disable channel hopping and fix the adapter on the target frequency. If we highlight our test AP on the list, we can now see we have one matching client. Take note of the network details like BSSID and associated client's MAC address, as this information will be fundamental in subsequent steps. Let's open our favorite text editor and paste the needed data. Here we are. After the initial recon phase, we can now stop AeroDumpNG, but we will restart it shortly, as you will see. We just need to lock it on the target channel and enable saving captured frame. To do this, let's type this new command. As you can imagine, we are filtering by network BSSID. We also supply the suffix for the output.cap file. Run the command. You will need to leave the AeroDumpNG window open through all the attack session in order to continuously collect wireless frames. Remember that we need to gather a sufficient amount of data frames to be able to crack the WEP key. Looking at the AeroDumpNG data column, you can notice that the numbers are actually increasing very slowly. The reported data frame rate is in fact 0. Even if we are getting some data now and then. This is because our network is almost unused at the moment and is thus not generating a lot of traffic as we would need. As you have learned, we have various strategies to increment data frames counts quickly. The simplest but still most effective technique we can use is the deauthentication attack, also called the deauth attack. By sending a series of deauthentication frames to both the associated client and the AP, we force association on the two sides. The AP releases reserved resources while the client closes communications and tries to reassociate the same network shortly thereafter. During the deauthentication reassociation process, only management and control frames are sent, so this traffic is of no use for our primary objective. What is not immediately evident is that Windows, but other operating systems as well, will refresh their internal network status information upon reassociation. DHCP requests will be sent, along with ARP messages, all encapsulated inside of encrypted data frames that we can capture with our sniffing interface. So let's try to deauthenticate our victim client. First, let's open a new terminal window. Now we can type the following command: AirReplay NG -0 4 -A, the BSSID, -C, the Mac client, and our monitoring interface of mon0. At the end of the command, we specify our monitoring interface. Now that we have it all, let's run the command. We can stop the flood after a few deauthentication attempts have been made. Shortly after the attack ends, we should get a spike on our data frame counter, followed by another stable 0 rate after client has reconfigured its new connection. While you could retry this attack over and over again, it would take a lot of time to collect enough data frames to be able to perform any of the exposed statistical attacks. So, we must use an alternative technique that can help us to increase the data frame rate and provide a constant flow of new initialization vectors. Let's introduce the ARP replay attack. ARP replay is a technique that consists of capturing a wireless data frame containing an ARP request and re-injecting it. ARP requests are broadcast messages. When one of these messages is received by the AP, it is immediately forwarded to all of the listening stations, but it is important to know that the AP first encrypts them using its pre-configured web key and a newly created initialization vector. If we were able to inject the proper ARP requests in the wireless medium, we could trick the network access point into sending a lot of useful data packets that, once we collected them, would give us the ability to finally crack the network key using PTW statistical attack. As you can imagine, the prerequisite in order to perform this attack is a valid ARP request frame must be sent by one of the active clients. How can we get our hands on one of them? Listening to the network traffic for a while should give us a chance to capture at least one ARP request, but we can also resort to the deauthentication attack we just tried in order to generate some ARP traffic. If you are wondering how we can determine ARP requests from an encrypted frame, it is useful to know that we can just easily identify them by the wireless penetration tools, as they have a fixed known payload size and a broadcast destination address. Now let's go back to the action. As you probably recall, a client cannot transmit data frame if it isn't associated to the AP itself. Of course, we could bypass this limitation by spoofing any valid client's MAC address, but let's try to follow a different path for these learning purposes. Along the way, you will also get a deeper understanding of the wireless protocol. We will use the fake authentication option of the Air Replay NG tool to let our wireless adapter authenticate and associate to the network AP. As the network is using the open authentication system, we don't need any additional information besides the SSID and the AP MAC address in order to obtain the association ID. Let's now open a terminal window. And so we can see the screen. Let's move it down here. Now we can type the following command. Let's copy the BSSID. We can also specify the SSID name, but it's not strictly necessary. The -1 flag at the beginning tells Air Replay NG we want to perform the fake authentication attack. 6000 is the amount of seconds between subsequent association requests, while -Q10 is used to send keep alive frames every 10 seconds. This is used to maintain the association state. Most of the times you won't need to specify this last option, and you would simply lower the attack level interval to 10 seconds. However, this variant is a more robust alternative and will work with the picky access points as well. Running the command, we can see an output message. This tells us that the association was successful. Shouldn't you get such a message, please review the network signal level, and if it's too low, try to move closer to the target AP and re-execute. Here you can see Air Replay is sending heartbeats to keep associations alive, so do not close this terminal window or you could lose the AP and cause it to reject all the frames you will be sending out. Instead, open a new one to perform the actual ARP replay attack. So let's fire up a new terminal emulator. Let's move the window down here. Now we can type this command in order to perform the attack. Air replay NG -3 -B. We use the MAC BSS ID and then our monitoring interface of Mon0. The Air replay NG syntax is pretty self-explanatory. You specify the ARP replay attack mode with the -3 flag and set the target network BSS ID using the -B parameter. Now we can run it. Upon execution, Air replay will wait until an ARP request frame is captured over the air. You will probably need to wait for a few seconds in normal traffic conditions. To accelerate the process in our testing environment, we will issue a ping command from the client to an unknown IP address. This will generate some broadcast ARP traffic frames. As you can see, just after the ping execution, Air replay NG catches an ARP request and suddenly starts to re-inject it into the network. Let's focus on AeroDump NG now. Data frame rate is now around 100 per second, and we are rapidly collecting preciously encrypted frames. As soon as we reach 5,000 data frames, we could already try to apply the statistical attack. What we will do now is speed up the video a little and return when we get enough IVs. Here we can go. We can open a new terminal, leaving Air replay doing its job at the same time, and launch AirCrack NG. You only need to provide it the WEP key length, the network name, or BSS ID in the source capture files. You can get clues about key length by inspecting the captured traffic, so you will need to take a guess. Luckily, only two possibilities are actually deployed in the wild, meaning 64 and 128-bit key lengths. A good strategy is to first specify a key length of 64 bits. If you're not able to crack the key, even with more than 20,000 IVs, then switch to the 128 bits and retry. Now let's run AirCrack NG. In our case, 10,000 IVs are more than enough. In a couple of seconds, AirCrack NG informs us of the results. We were able to successfully determine the network key. It didn't take too much effort at all. The previous scenario showcased the classic WEP attack scenario. Now we will try to spice things up a little by enabling shared key authentication on the access point, adding an additional client into the game. We have already reconfigured the network settings of our environment, and as you can see, we set up the attack machine desktops so we will not need to waste time on window management. Let's start then by observing the situation from AeroDump. We already focus on channel 11. And we also filter out all networks but ours. AeroDump NG still shows WEP as the configured cipher, but note that the authentication column is still empty. In fact, AeroDump cannot directly determine the authentication method in use just from the AP beacons. Instead, it needs to listen to at least one authentication message flow in order to identify it. This is the reason why you get an empty column at first. So could we just proceed as before? Let's try the fake authentication attack. Launch the same command we used in the previous scenario. Air replay NG tries the authentication process against the network, but its attempt is refused because the network is using a shared key authentication. If you recall from the slides, to successfully complete the shared key authentication process, a client is required to encrypt a challenge text received from the AP using its configured WEP key. The AP can then compare the decrypted text with the original value, and if they match, the authentication concludes with a success message. This version of Error Replay automatically switches to shared key authentication, but given we didn't provide any key stream, it resorts to a fragmentation attack in order to get some. We just stopped it, as we will pursue another way. There is in fact an alternative method that can be used when at least one associated client exists in the network. This is called MAC spoofing and consists in setting our wireless card's MAC address to match the one of an actual associated client. Changing your card's MAC address requires you to stop all processes using the monitor interface, so we should close AeroDump-NG, but first let's note down the MAC address of both associated clients. After that, we disable temporarily the monitor interface by issuing the ifconfig mon0 down command. At this point, you can safely change your adapter's MAC address with the MAC changer utility included in the Calix Linux distribution. Type MAC changer -MAC. Paste the MAC address of one of the identified clients and specify the target interface of mon0. Upon execution, the command confirms that the card was assigned the correct MAC. You can further verify this by running the ifconfig mon0 command. Looking at the HW address field in the output, as you see, it does reflect the desired address. So now we can bring the interface back up. To do this, we'll run the ifconfig mon0 up command. Please note that this command could take a few seconds to complete. From this point forward, our wireless monitor interface will use the newly specified MAC address when injecting frames on the wireless medium. This way, all those frames will look like they have been sent by a legitimately authenticated client, and so will not be rejected by the AP. Of course, should the target client leave the network, you would have to change your MAC address again or rely on a different attack strategy. The important conclusion is that the classic ARP replay attack would now work without running a fake authentication before, so this is a big time saver in most cases. But instead of showing the technique we already used in the first part of this video, we will try something new. As an alternative to capturing one ARP request, we will try to forge our own using the Packet Forge NG tool from the Aircrack NG suite. If you recall from the slides, this is not normally possible until you don't get a long enough keystring, which then you'll use to encrypt the ARP frame. In the slides, we talked about the fragmentation attack and how you can use it to recover a good amount of the keystring. There is a lesser-known alternative to the fragmentation attack, which is called the chop-chop attack. The chop-chop attack's working mechanism is quite intuitive and relies on the insufficient message integrity protection implemented in WEP. You should recall that the WEP provides only 32 bits of CRC code known as the integrity check value in the encrypted data footer. Korik, a user active on the NetSumler forums, discovered some mathematical relations between the last byte of the encrypted payload and this integrity value, and he also developed an attack. Practically, upon capturing a data frame, you can strip 1 byte at a time from the payload and be able to recover 1 byte of the keystring. Repeating the procedure with the shortened frame, you can recover 1 more byte and so on until you obtain the entire keystream used to encrypt the frame. The outlined algorithm gives the name chop-chop to the attack. One big advantage of the chop-chop attack over the fragmentation attack is that at the end, you will not only recover some useful keystream bytes, but you'll also decrypt the original frame. We will soon describe how we can exploit this useful property to enhance the reliability and efficiency of the ARP replay attack. Let's see how we can perform the attack with AirReplay NG. From a terminal window, let's type this command: AirReplay NG -4 -B, the BSS ID, and mon0. The syntax is similar to other commands issued before, but this time we are specifying -4 as the attack mode. As you can imagine, it instructs the tool to use the chop chop attack. Let's run the command. Upon execution, Air Replay listens for a traveling data frame. When a data frame is captured, Air Replay asks us if we want to perform the attack using that specified frame, like you can see now. Please note that not all the frames are good for this attack. We need to recover at least 68 bytes of keystring to encrypt a full ARP request. You can read captured byte length on Air Replay output, so check that it's bigger or equal to 68 before confirming the frame. If the length is less than 68, just skip the frame by pressing the end key. When you get a good candidate frame, you can confirm it by pressing Y. The attack will then start. In our case, we got a 106 byte long data frame. We are good to go, so we can confirm the message. It could take a while because the chop chop attack needs to make several guesses in order to discover the value of the stripped byte, so it can send more than 200 frames for each single frame byte, or even more in bad signal conditions. The distance from the AP is a very critical factor since you need to be able to listen to the accepted frames in order to succeed. As we can see, Air Replay is proceeding 1 byte at a time from the last offset. Every byte apparently requires about 10 seconds in our environment, so we will speed this up for you. Here we are. In our case, the attack took a couple of minutes to succeed. The replay informs us that it was able to decrypt the target frame and saved it in the specified file. Also, we recovered 106 bytes of the key stream that has been saved in an XOR file. Now that we have collected the needed amount of keystream material, we can forge our ARP frame. Aircrack NG Suite comes with a tool that has been purposely designed for this task, which is called Packet Forge NG. Any ARP request contains 2 IP addresses, the target IP address and the sender IP address. If we want to get the best results from our ARP replay attack, we should use IP addresses that are relevant for the target network. You could obviously make some educated guesses by looking at the AP default configuration settings or testing popular private IP address ranges. These are all good options, but in our case, we were just able to decrypt 1 data frame. So let's have a look at it to find out the information we need. For this task, we can use a command line packet capture analyzer, the famous TCP dump. Write TCP dump -n -r and specify the file name or path of the decrypted data frame. Here we are. The packet captured was sent over IP. You can see the network is using the 192.168.0.0 subnet, and we also identified 2 different IP addresses. One is 192.168.0.3 and the other is 192.168.0.1. With this information, we can now finally forge the ARP request. Let's type the packet forge command and then describe the options used. The -ARP command at the beginning obviously indicates that we want to forge an ARP frame. Then we specify the AP's BSSID, the client MAC address, and the 2 IP addresses. The first one represents the target IP, while the second one is the sender IP address. We pass the command the captured PRGA to encrypt the frame, and finally specify the output file. Let's run the command to generate the frame. Once we have forged the ARP frame, we can inject it, but first we turn on AeroDump NG again, this time saving the captured data to a file. Now our dump is alive and capturing, we can inject the ARP frame using a replay special interactive mode identified by the -2 option. With the -R option, we specify the source file from which to read the frame to inject. Now let's run the command. Just confirm the frame as it is the only one in the source file that we had specified. If you've done all the steps correctly, you should now see that the collected data frames number increasing very fast. Take a look at our AeroDump.ng window. While we are capturing, we can already start AirCrack.ng. The program will continuously read captured data during the execution in order to work with the higher possible number of frames, improving cracking speed and success chances. We use the bottom window for the purpose. Here we input the file name of the AeroDump.ng capture file. AirCrack.ng can now start. We'll speed things up a bit for you while the cracking goes on. Here we are. As you can see, we were able to recover the key, but this time we needed almost 20,000 data frames in order to succeed. Given the fact that we were using a different router from the first part of the video, this is probably due to inner protection mechanisms implemented by the new one. Nevertheless, it didn't take more than 2 minutes to crack the whole thing. We have reached the end of the video. We managed to demonstrate various useful attack techniques that you could adapt and use in a number of different scenarios. In fact, reality could be much different than that of your home test environment. With the proper tools and the deep understanding of the attacks that comes with a careful study of the course, you will be able to succeed even in the most unlikely of situations. Thank you for joining us.